This is going to be the start of where the videos are going to become much more abridged. I'm not going to go through full solutions. Part of that is to combat the senioritis that a lot of people are feeling, and I've kind of noticed it with some of the homeworks lately that people are not really trying the problems on their own. They're just kind of skipping to the end of the video and just writing down what's on the screen. So I'm going to work to change that by making these videos more of you doing work and less of me doing work. So for this problem, number 56, the crankshaft inside an automobile engine is initially spinning at a rate of 1800 RPMs. This rate increases to 5000 RPMs in 2.4 seconds. And in part A, you want to convert both given angular speeds to the standard units of radians per second. So with the 1800 RPMs, that's the same as saying revolutions per minute. You want to multiply that by two conversion factors. One, which is going to convert revolutions into radians, and I'll leave it up to you to figure out what goes in front of them. That's straight from your notes. And then the second conversion factor, that will turn minutes into seconds. And then since revolutions is in the numerator, that's why it was in the denominator down here, and minutes in the denominator cancels with the numerator up here, and you're going to be left with units of radians per second. So you just want to do that for both the 1800 and for the 5000. For part B, determine the angular acceleration of the crankshaft while it is spinning at 1800 RPMs. So just think of this in terms of when we did translational kinematics. This is spinning at a constant angular velocity of 1800 RPMs. So what's the angular acceleration? The same way that if something is moving at a constant linear velocity, what is the linear acceleration going to be? So it's a pretty easy one to figure it out. That's why that question says to determine it rather than calculate it, because there's no calculations involved. Part C, calculate the angular acceleration of the crankshaft during that 2.4 second time interval as it's going from the 1800 RPMs to the 5000 RPMs. We already converted those back in part A, so whatever answers you got for those are going to be your values of the initial angular velocity, whatever that 1800 was once you converted it into something else, and the final angular velocity is going to be whatever that 5000 was once you converted it into something else. The T is the 2.4 seconds, and you're trying to find the angular acceleration, that is the alpha. So just pick the appropriate kinematics equation. That's the one that is missing the delta theta, which is the first kinematics equation, and you should come up with the answer given the 139.6 radians per second squared. For part D, calculate the number of revolutions the crankshaft makes during that 2.4 second time interval. So I would go to the original three pieces of data that were given, these three right here. Don't use the alpha you just calculated, just in case you happen to get that wrong. And now you want to solve for the delta theta. So delta theta is your unknown item, and you want to use the rotational kinematics equation in which alpha is missing, which is going to be that second one on the list. And when you use that equation, you will get an answer that is not what is the answer on the sheet. Because it says 136 revolutions on the sheet, you're actually going to get an answer in the proper units of radians. And then you've got to use the fact that one revolution is equal to 2 pi radians in order to convert to get the answer of 136 revolutions. Part E and F are both proportional reasoning. You're going to use the formula you used in part C, that same formula used in part C, to answer part E, and use the same formula that you used in part D to answer part F. And in both cases, just cut the time in half and see how it affects the angular acceleration, and then how it affects the number of revolutions. And finally, for part G, you're going to give graphs of angle, angular velocity, and angular acceleration. We have not talked about the graphs in class, but they act the same way as the graphs of position, velocity, and acceleration when we're talking about translational or linear motion. So let me just quickly show you the graphs for linear motion. just to remind you. Now it says in here that the crankshaft is spinning clockwise, and if you remember from your notes, one of the important things is that clockwise refers to the negative direction. So think of this as an object moving initially with a constant velocity in the negative direction, and then it's speeding up in the negative direction, because this item is spinning in the negative direction, and then it's speeding up its rotations in that negative direction. So if you were to graph position in the x direction, that will be something where it starts at a certain position. I'll just start at 0. And initially it's going to increase at a constant rate, increase in the negative direction at a constant rate. And then when it starts accelerating, it becomes, the graph looks like concave down, like that. So that part where it changes over, that's the TA, the part where it begins accelerating. So what does the velocity look like? Well, initially it has a constant velocity. So up to the TA part, you should have a constant velocity in the negative direction. I'll leave it to you to figure out what that looks like. And then that velocity starts increasing in the negative direction. So you can figure that out. And then finally and that one should be acceleration, not time. What does acceleration look like if an object is initially moving at a constant velocity in the negative direction? Well, constant velocity, that tells you something pretty obvious about the acceleration. And then it starts speeding up in that negative direction with a constant negative acceleration. So what will that graph look like?